Okay, we're going to get started. My name is Jim Butler. I'm with the Kansas Geological Survey at the University of Kansas, and it is my distinct privilege and great honor to introduce the 2013 Darcy Lecturer, Dr. David Rudolph. And before letting him take the stage, let me just give some background information on Dave. Hydrogeologist of great prominence, so we're very fortunate to have him serving as a lecturer this year. Now, Dave got his start. He's from Canada, so it's a foreign lecturer this year. He got his start in geological engineering and then went on to hydrogeology. So he's combining science and engineering, which is very appropriate given the Science and Engineering Division of NGWA. So he's a great representative not only of the division, but of the organization as a whole. His undergraduate degree is in geological engineering from the University of Manitoba, which is apparently in a city called Winnipeg. Well, frankly, I have no idea where that is, but I'm gathering it's in Manitoba. Yeah, okay. Then he went on to the University of Waterloo, where he ran the table in terms of graduate degrees, both MS and PhD in hydrogeology. And then from that point on, he has worked at Waterloo as a professor, and again, has made some great contributions, so it's very appropriate that we honor him as the Darcy Lecturer. This is his 56th and final lecture. So this is an arduous ordeal, and he has handled it extremely well. Currently he's a professor in earth sciences. He's cross-appointed in civil engineering, so again, that link in the science and engineering. And his presentation is entitled Managing Groundwater Beneath the Agricultural Landscape. I have heard him give this presentation in Germany and in Kansas. This will be my third time, and it is a real pleasure. It's a presentation that has both the breadth and depth that's expected of a Darcy lecture. And so without further ado, please join with me in welcoming the 2013 Henry Darcy Distinguished Lecturer, Dr. David Rudolph.
Well, thank you very much, Jim, and thank you all for being here. I will apologize right up front for my Canadian accent. So you'll hear a few A's in there, a little bit of that, this and that. And just as we get going, let me first of all obviously thank the National Groundwater Association for the privilege and the trust to be on this lecture series for the course of the year. It's been an unbelievable experience. And also to the foundation, obviously, for providing the support, the financial support to allow this tour to occur. I think it's a great thing for NGWA, and it's a wonderful thing for all of us as a group. This year, we also had support from a couple of other groups. So Integral Consultants and Regenesis were very gracious contributors to the costs of the trip. Some of the traveling, and the University of Waterloo also contributed to it. So thanks very much for that. So being here today is a little bit like being at the home rink after being on the road for a long time. So it's kind of nice to be here. But I brought a few little statistics, since this is the end of the road, that this group might be interested in more than the other 40 or 55 locations. So let me show you a few of those. First of all, where did the tour take us? So this series of maps shows you the locations, the little red stars, and sorry, this is sort of a really odd angle for a laser pointer, but the red stars indicate where in North America I had a chance to visit over the course of the year. The panel on the right shows you Europe, 8 or 9 or so locations throughout Europe, and a very interesting tour through Australia. I'll share one little tidbit from that particular tour in a moment. So all of those together, about 47 sites. I postponed a few of them to the new year, so I've got a couple going off into the new year here, probably 5 more of them that I had agreed to do. But for the most part, this is the last one for 2013. So I just wanted to provide you some insight as to what what the lecture involves. So this is what I call the Darcy Lecture by the numbers. So the first statistic is the mileage. So my best estimate was that there was about 73,000 air miles as part of the trip. Another statistic was, I think we've calculated it out, a little over 3,000 people attended the lectures over the course of the year. That involved almost 110 hotel room stays. Carrying on from that, about 81 flight segments, just as an example. And as we mentioned, that number of lectures and sites, and the last couple of statistics, and I think Jim was maybe just a little bit conservative. I think Jim and Scott King had to sit through, I think, closer to 6 times when I calculated it, Jim. So that is solidarity right there, I must admit. Oh, and by the way, just as a tangent, Jim Butler attended his very first NHL hockey game last night, and I took him there. And we sat in a location where I was hoping to be able to get a puck for him because he'd never been before. So since we didn't catch one, I ended up getting one for you. So there's the Thrashers, and it says on the back, Vancouver Canucks 3, Thrashers 1. Something to keep on your table there, my friend. By the way, that was a good catch. That's a little bit better than Luongo, actually, when I see you do that. Yeah, that's right. Oh, and one last one. One very relieved Rachel Geddes, who's been looking after this. Is Rachel, did you stay here? She was here, and now she's gone. Anyway, she did a phenomenal job arranging this. She's just a great contribution as a staff member in organizing the tour throughout everything else. So just an indication of how the tour looks from a number point of view. The other thing is that as you travel around a little bit, you see different things. And during the trip through Australia, I realized that when they have their groundwater meetings, they have certain protocols about sampling water wells and monitoring wells. And they demonstrated one in the field to me. And that was, this is about a foot across here. So this is what you have to learn, is that all monitoring wells are protected by guardians. And you just never know who's going to be there when you show up. That is a very much a baby huntsman spider. So that's about as small as they get. The biggest ones would probably stand more or less on the top of the whole case, top of the well cover here. So you have to be very careful as you're moving around. Those are things we don't normally have to take into account, but something you would see when you're in Australia. So the tour, of course, is dedicated to Henry Darcy's contributions, and what we normally deal with as practitioners, of course, is his famous rate law that helps us understand and quantify movement of subsurface fluids. But at the time, of course, that Henry Darcy was active, he was much more well-known as a very practical water resource engineer working on problems very similar to what we do today, developing water supplies for urban centers, managing water resources for irrigation, a whole variety of problems that very similar to what we deal with today. And it's really in that context, if I can, I'd like to cast the lecture for today. So the title is quite broad in a sense of managing agricultural development in a ground with a concern towards groundwater management. But in reality, it really gets to the let's say the societal demand of having food security into the future. And that particular challenge is one that's pretty generational. It's been passed on to various generations with challenges that have been uniquely distinct to that generation. Providing enough water for irrigation, opening up the western part of the United States, getting water into the area to irrigate, having enough fertilizer for crops to produce higher quantities of food. All of those were different generations of problems that came along. Currently, our generation is probably dealing with this management of agriculture and the future of it more related to integrated water resources and water resource management than it ever was. So I would say that our role as a group is particularly important now and will be in the near to probably distant future. So I'll cover certain aspects of this particular project and concept, specifically looking at how groundwater and agriculture interact, some of the roles that they play together, and problems that we might face in dealing with this. So let me get started just by giving you some statistical background, and I think this helps with some context. First of all, as you might imagine, all of our very good arable land is developed for agriculture where it can be. And in fact, we develop a lot of land that's not what you'd consider very good for agricultural development. In fact, desert areas that are reclaimed and turned into agricultural, intense agricultural areas. The Central Valley in California is an example of that. Much of Israel that's developing and leading the way in drip irrigation in really sandy, poor, permeable soils with not much precipitation. But almost half of the Earth's surface is involved in some type of agricultural land development. So you can imagine how much of our recharge moves through an agricultural, both from a quantity point of view and a quality point of view. So lots of our land is engaged in that. What also is probably not surprising is that agriculture is a very demanding water land use. So, of course, the first thing that comes to mind is irrigation, but that's not the only area and avenue that water is used in. But clearly, when we look at the statistics of it, a major component of the global water withdrawals, fresh water obviously, is used for agriculture. And because if it's designed correctly, irrigation is by its nature consumptive in a sense that if we apply it to the ground, the plants will use it and put it back into the atmosphere where it's then free to move away from where we took it from. It may rain out again on the ocean, it may rain out again somewhere else, but it's consumptive in the sense that it moves away from where it was withdrawn, so we refer to it as consumptive. Another point I think that's useful, we frequently use this date 2050 as a projection for how we might see changes within the climate variability over time. So 2050 is a target people talk about. But if we look at it from the point of view of food demand, the most recent statistics will indicate that from today until 2050, we may see an increase of close to 70% in the requirement for food. A lot of that relates, of course, to our population increase, but it also relates to the fact that our demand is changing throughout the world. So Asia is demanding more protein-rich food. Lots of changes coming down the pipe in that sense. And of course, with that comes an increased demand in water. So a significant increase in what we're using right now, which is already very high, thinking that most of our surface water sources are either allocated, in many cases over-allocated. A lot of that will come from water reuse, and a lot of that will come from groundwater. So we can imagine that type of a pressure on it. So from a quantity point of view, you can kind of get an idea of how significant managing water will be in moving forward with agricultural development and food security. Of course, there's the other side of that coin, and that is that what we do with land management can influence water quality. And this is more or less how this generational change is occurring as we're understanding more and more how that large area of land use management is influencing us from a quality point of view. So often you'll read statistics that will say that agriculture as a land use practice represents probably our biggest pollution factor that one can come across for water. And the categories that we often consider are nutrients, so phosphorus, nitrate, what you frequently hear about, other chemicals like pesticides and agrochemicals people use to keep cropland as healthy as possible to maintain production, and some of the emerging contaminants that we deal with now, pathogens derived from manure and solid waste application or biosolids, and pharmaceuticals, things coming from the production of animals that we're starting to see in the water courses here. Of course, so what we do in the ground surface here really is designed to work in the top meter or so, but in lots of scenarios, we're draining the top of the water table. In this particular case, here's some tile drains that are feeding directly into this surface water source. So these drains are like a plumbing system that short circuit whatever leaches through the root zone into these tubes and out into the surface water very quickly, bypassing the riparian zone. So the dynamics of how water moves through the agricultural fields is a challenge and something that we need to understand. For today's lecture, I'm going to focus primarily here on the nutrient component, and we'll take it from there. And just another little context point. Interestingly, just last year, your National Academy of Engineers, who frequently look across the landscape to see what major challenges are facing humankind now, listed the management of nitrogen particularly as being one of the grand challenges that we face. So that kind of puts it in context in terms of scale. So how did we get to that stage? Well, thinking back to the idea of a generational change in how we manage food and deal with these issues, back at the turn of the century here and earlier on when Henry Darcy was active back here, you can see that the amount of reactive nitrogen that was available to be used for things like fertilizer and other applications of it was pretty small. It was mined in Chile. It was put together from animal manure and bat guano and things like that. There just really wasn't that much of it. And at the turn of the century, here's a picture of two happy-looking guys up here, had a major breakthrough that often people refer to as the most significant experiment ever conducted. And that was to be able to produce a form of reactive nitrogen literally out of the air. So taking atmospheric nitrogen and oxygen and through a reaction process, generating a source of soluble and reactive nitrogen here that could be used for any type of application. And as you can see, as we get to the end of the Second World War here, the production of that went up exponentially. And along with that, of course, as you can imagine, you can parallel and place on it the population growth. So one can say either this particular generational solution was to be able to provide the fertilizer to grow the food, to sustain that growing population, or that growing availability of food allowed that population to grow. One way or other you look at it, it resolved it. But the legacy of that, of course, with that changing the nitrogen cycle so significantly, taking it out of the atmosphere and putting it into the terrestrial system at a very, very high rate, most people will agree was much more significant than the modifications to the carbon cycle. So as a result of that, the Academy of Engineers are saying nitrogen management is a severe and serious issue for all kinds of reasons. And let's look at a couple of those reasons. The first one that you probably are quite aware of because you see it frequently and the public sees it, is excess nutrients arriving in surface water bodies. And that was a problem people tracked for decades in relatively small water courses, in wetlands, in streams, where nutrients were arriving at these water courses, and they didn't have the ability to assimilate all of this nutrient. So the excess nutrients resulted, of course, in the excess growth of algae and vegetation in the water, causing the consumption of oxygen in the process of eutrophication. So a very significant impact on ecosystem health. And the issue here is that that's moved up to be a much broader scale problem, to very large surface water bodies. So on your right-hand side is another photograph here. And in this particular case, this is the shoreline of Lake Winnipeg. There, you've heard that word twice now today. Lake Winnipeg is one of Manitoba's Great Lakes. It's an enormous lake that over the last 5 to 10 years has systematically started to have huge algae growth in them. So large algae plumes covering major portions of the lake, believed to be primarily related to agricultural runoff, mixed with urban runoff coming up from the city of Winnipeg. But the idea now is that these large water bodies, including lakes as large as the Great Lakes, are being influenced by this excess nutrient problem. And we go as far as embarrassingly having this wonderful award we got this year, as that particular lake being the most threatened on the planet for 2013, which is not a great thing. And I know what you're thinking. It would be great to visit Winnipeg. So I made this map up specifically for you folks. And I typed in wonderful vacation spots in North America, and Expedia sent me back this. And you can see Winnipeg there. Whoops, let me back up a little bit. You can see Winnipeg sitting right in the middle there, and that's Lake Winnipeg. So that's that large lake, another one beside it, Lake Manitoba. So those are the listed hot spots. So there's a few on there you might recognize. Salem, Oregon, Gary, Indiana, others that you frequently would like to get to. Sioux Falls, there we go, and Winnipeg. So I thought, just in case you didn't know where it was, there's the thriving metropolis of Winnipeg. So from a surface water point of view, lots of research going on that. There's lots of pressure on it. The International Joint Commission quite concerned with nutrient loading to the Great Lakes, and we're seeing that type of influence worldwide. From our point of view as hydrogeologists, the other, I guess, side of the coin is what the impact is on the subsurface resource. This particular study, it's just an example of many that are around and available to learn from, was completed by the University of Davis researchers a year or so ago. Tom Harder and colleagues working on this, they were asked by the California government to try to evaluate what the status of nitrogen nitrate primarily in their drinking water resources were. So they did a very extensive study of that. I've just taken one diagram out of their report, and this shows the occurrence of elevated nitrate in drinking water wells. And these are not just private wells. These are relatively large public supply wells. And to the surprise of the authors and the studiers, they found that 1 in 10 of these large public supply wells were exceeding the drinking water limit for nitrate. So this is in the Central Valley here. You can see on the far side, if I can point the laser pointer correctly, here in California. And so the issue is here, it's moving from a sort of a private small well problem up to a large capacity well problem. And of course now this is an issue for human health. So as hydrogeologists, when we study this problem, it's relatively challenging because of its nature. So we refer to it as a diffuse source problem or a non-point source problem. So the way one would define that is, imagine we've got a production public supply well here, and here's an air photograph showing the ground surface, and each one of these little pieces of land is a farm. Maybe a farmer runs several of those pieces of land, but each one of them will manage that land a little bit differently. They'll apply fertilizers at different times. They'll use different types of fertilizers. The topography is going to be different. The subsurface geology will be different. And as a result of that, the loading function of excess nutrients that are applied on this field are anything but uniform. They're highly irregular where they get into the subsurface. And on top of that, if you look at a little bit more detail into it, what you'll see, of course, is the complicating factors that influence this are, of course, this application irregularity over the surface and lots of subsurface variability, as you can see from this cross-section, but also from the fact that the hydrology changes during the course of the year. We get precipitation events, and then we get winter time, and then we get spring melt. So what's driving that excess nutrient into the subsurface, of course, is very dynamic. And on top of that, we're frequently asked to determine the area that's actually contributing to that well, which is not an easy problem. In fact, I would say that's probably the classic of all non-point source problems, trying to determine if in fact the capture zone looks like that, or if it looks like that, and when does it look like what, depending on the course of the year. Of course, it's always moving, as recharge is very, very dynamic, and that's what controls it. So that in itself makes this non-point source problem of agricultural impacts to water quality complicated. And one other thing we can place on that is the fact that no matter what we do on the ground surface, it has to find its way from the ground surface down to the water table. And as it does that, it migrates through the vadose zone, or the unsaturated zone, which is a process that's very, very dynamic and heterogeneous on its own. And I'm just pointing it out because we'll make use of this as we move along here. So just imagine that fertilizer was applied at the surface here, and it moved down through the root zone, and it'll move down until it stops from how much water was applied, and that water will be distributed in the unsaturated zone, and it will stop moving. For it to move again, we need another precipitation event that will infiltrate, pick it up, and displace it downwards. So in reality, that profile represents, if you will, an archive, in many cases, of multiple years of applications of fertilizers at the ground surface. So what we do in this current year may not reflect at all what's hitting the water table at that particular time because of the time lag of travel. That's a very thin, unsaturated zone down to the water table. You can imagine it being much thicker than that and much more heterogeneous. So the unsaturated zone provides us with a challenge. And just if I can get this little video to work, I'll share with you sort of a little experiment that we used to try and get this, see if it will work here. It worked earlier. Sorry, folks, maybe it's not going to work. Should have plugged my computer in. Anyway, what that little video showed, it's not boding well here, is that if you apply this slowly at the surface, it will infiltrate into the subsurface and move down, and in a matter of an hour, it will stop moving. So even under a very significant recharge event, it will not go very deeply into the subsurface. So let's get past that little video and see if we can use another one here. Challenge then that one is faced with is how do we manage to maintain the quality of the drinking water resource in the face of needing to manage the agricultural landscape as best we can in terms of getting the optimum food production out of this. The stress on the agricultural landscape is not going to reduce, and it's sort of our challenge to be able to see if we can maintain the public drinking water resource in the quality of it in a way that we can maintain it sustainably. So just as an interest point, the USGS just published this document a few months ago, and this looks specifically at the vulnerability of drinking water wells and how water quality can be used to predict it. It's a very interesting document. If you're looking for information on well vulnerability, that's an example of the type of work that's going on. Very, very well done. Other types of studies that one will find internationally, here's one on the left side. This was completed a year or so ago by the European Union, and they were also looking at the impact of nutrients throughout their water cycle. They were looking at the effects, the policy dynamics of it, different sources, primarily from a surface water point of view. The Canadian government recently commissioned a study throughout Canada to look at that same impact of how we'll be able to sustain agriculture as time goes on. When you look at those reports, what they normally provide you with is an estimate of how to kind of manage this, and the approaches tend to fall under one specific category. That's something we would refer to as BEST, which I think is not quite the best term, or beneficial management practices that agricultural managers can adopt. So really what this works out to being is large-scale land use management of nutrients that will optimize the plant growth but minimize the loss to the subsurface. So the ways that people do that are applying nutrients at the right time, the right type of fertilizer and amount, as you might imagine, rotating crops appropriately in the landscape, using things like cover crops to provide excess amounts of green manure, if you will. The plants will decay in the spring, release organic nitrogen, and provide some of the fertilizer that the plants need. So those are really the approaches that people are taking. And the problem from our point of view is that there's very few studies that I can easily pull out and show to the agricultural community that, in fact, these approaches really work. And one of the main reasons for that is that concept of what happens through the unsaturated zone. What we do on the ground surface literally takes years and sometimes decades before we'll actually see that change at the water table, and even longer at a municipal or a public supply well. So we've got a real problem in our hands in being able to provide evidence, science-based evidence, that we can use to encourage farming operators to adopt these types of techniques. So as hydrogeologists, we need to find a way that will provide us with a metric to say that what we're doing out here is actually improving things. That's the first point. The second one is to convince operators that we need to monitor this for a while. It's not going to happen overnight. They have to adopt this. Government is not very happy with adopting long-term solutions to problems. So that time lag is a real difficult thing for us. So what we commonly do, of course, is rely on numerical modeling to predict what will happen. So as a challenge, what we have to do is provide and build the data sets and the information that will inform these models in such a way that the agricultural community will accept what we're providing and keep the uncertainty within a limit that we can understand. So that's really what our challenge is to be able to make some predictions here that we can sell to the agricultural community. So what I'm going to show you now is the results of essentially a decade's worth of research, particularly on this problem. And the group that I'm going to share the results from is this group of 11 graduate students here, and you'll meet them throughout the course of the rest of the presentation. They all provide a certain aspect to this study. And interestingly, from a point of view of training and disciplinary approach, you can see the diversity of skills that this group brought to the table. So in handling these types of large-scale problems, physical hydrogeology, contaminant hydrogeology would be a given, but understanding dynamic hydrology, agronomy, microbiology, numerical analysis, all of those pieces had to be come together in order to resolve this problem, and this mixed group was able to provide that. So there's a whole bunch of them outstanding in their fields, doing things. And I'd like to focus primarily on their observations in the field because I think that's some of their greatest contributions here. And I'll just say that that's what they wanted me to remind you of. So let's see if I can actually get this one to work here. No idea why their videos won't work here.
Are they in the same folder?
Yeah, they're all in the same folder. That's really, really strange. Give me 1 second. I'm just going to throw this slider in. I wanted to illustrate that to you. It actually worked before lunch, so let me just show you this because I've got a couple of other videos that are probably worth looking at here. See if I can get it to work. Maybe it's not worth the whole hassle. Anyway, what I was going to try to do, I'll walk you through it, was to fly you up to Ontario. So Google Earth allows you to do that, and since we can't do that, I'll just take you there quickly. And here we are in southern Ontario. So this part of the world, which takes a little while to fly up, but not very long in Google Earth, represents the one of the densest populations in Canada, and as you can see, is completely surrounded by an ocean of fresh water. So there's the Great Lakes network sitting around it here. And this area here has been recently glaciated, and the majority of the drinking water supplies for the large cities like Toronto and Chicago, of course, are drawn from the Great Lakes, but all of the other cities that are in this densely populated area here draw their water primarily from groundwater resources. And they draw them from the overburden, the glacial overburden, which ranges from 0 at the Niagara Escarpment, where Niagara Falls falls over a very steep cliff here into the lake, and to maybe 200 to 300 feet thick, mixed glacial till units with sand and gravel outwash features that make wonderful integrated aquifer systems, very complex systems, but very good water supplies. Underlying that overburden, that glacial drift, is a fractured rock and aquifer that's used throughout the province as well. Both those resources are developed to supply urban supplies for the cities. Now, one of these cities that I want to take you to, which we would fly down to but won't work today for us, is the city of Woodstock. So this city is a population of about 50,000. It sits almost right in the heart of the Southern Ontario Peninsula, so a long way away from the Great Lakes. Building a pipeline out to the lake would not be feasible for them, so they rely completely on groundwater. And their one of their major well supplies, still their primary well supply, sits outside in the rural area, surrounded by agricultural development here. The wells are approximately, 100 feet or so deep in the glacial drift, and they provide something like 200 to 300,000 gallons a day, each one of them, as the public water supply. So this particular location has some unique aspects to it that make it worthwhile at studying. This plot on the left-hand side shows you the quality, particularly for nitrate, in that group of drinking water wells embedded here in this little woodlot. There's the city of Woodstock up here. And over the course of about 30 years or so, what you can see is this progressive increase in the concentration of nitrate. And this is nitrate as N. So the drinking water limit that I've got noted here of 10 milligrams per liter would be 46, 47 as nitrate. Okay, that's the same drinking water limit we have in Canada and the United States. So this is very typical of this non-point source or chronic type of contaminant source. Very slow increase as the wells capture more and more of the effect of the land around them, and the concentration progressively increases. By the time we got to the mid-1990s, 3 of these wells, particularly these ones here, exceeded the drinking water limit for nitrate. At that point, of course, the municipality was stuck with a dilemma. They couldn't provide that water directly to the houses. They had to do something with it. Fortunately, they had a couple of other wells. They were able to blend it to keep it below the drinking water standard. But of course, they were worried about the fact that it was going to get more and more concentrated, and what could they do about that particular problem. Well, the main option, of course, was to build water treatment. So a treatment plant to remove that nitrate would have cost anywhere between $10 and $15 million to build the plant. Then it had to be operated on an annual basis. So the councillors looked at a different option. They decided, instead of opting immediately for drinking water treatment, that they would try to adopt a best or beneficial management practice. And what they adopted was to purchase some land in the vicinity of the capture zone around the wells, and then very, very carefully manage the nutrients on that piece of land. So they hired expert agronomists to tell them what would be the optimal amount of use of nutrients to get a very good productive crop off the field, but to minimize the leaching of and loss of nitrate particularly. So what they're really doing here is making use of, or hoping to make use of, an alternative or best beneficial management practice as an alternative to building the water treatment plant. Okay, so this was the approach that they took. Interestingly, instead of putting that land out of production, which they could have done because they owned the land, they decided to maintain it in production. Their whole community there is agriculturally based. So their idea was, could we keep this land in production and at the same time solve our problem of this exceedingly high concentration of nitrate in our production wells? So let's take a look at that. There's the two pieces of land that they purchased here, about 300 acres in total. There are the production wells right there. And it was deemed to be sitting within the 2-year time of travel. Now, what we would normally do to calculate that would be apply a model like ModFlow, do a particle tracking calculation of it, and determine that water in the aquifer on the outside of that dashed line would take longer than 2 years to be captured by these wells. Water on the inside of that envelope would be captured by these wells in something less than 2 years. So you can see that those two pieces of land are sitting there, which would indicate that that influence would be obvious in a relatively short period of time. So that's what they adopted. And let me just briefly show you what the change was. So here are our historical practices, and here were our modified practices. And really, they changed the crop rotation recommendations for it, reduced fertilizer application by about a half, replacing it with cover crop nitrogen through red clover and rotating the crops appropriately. And this routine then was intended to just provide enough fertilizer to keep the crop going at an acceptable return rate and crop yield. Okay, so you're seeing that almost half of the commercially applied fertilizer was reduced. So the questions that they asked us as hydrogeologists then were, could you determine for us what benefit that had in terms of the loss of nutrients under that 300 acres of land? In other words, how much is leaching now? And if we change these practices, how much will that reduce our leaching losses? That was the first task the students were challenged with. The second one was, if you could do that, can you tell us, will that affect our water supply wells or not? Will that be enough? We bought 300 acres of land. What's that going to do to our water quality? We understand that the wells are drawing water from a much broader area than that, okay? And the third part of it, almost as an afterthought, was, and tell us more or less how long that will take before we can have our system back in operation. Those are the challenges that we had. So let me show you some information that will help to understand the approach. The first stage of this, of course, was site characterization. So a series of wells were installed. That dashed line, black dashed line, represents the area that was purchased by the municipality. And each one of the yellow dots within this picture here represents single wells or multi-level wells that were drilled, cored, so we were able to determine the stratigraphy of the subsurface, installed the wells to get water quality, hydraulic head, measure hydraulic parameters one would need to develop a numerical model. So what you'd say is conventional site characterization occurred at this location. Something like 130 or so wells were installed in that first phase there. The blue dots, of course, just being the municipal supply wells. So information also that's useful, if we look at the topography, the red being high elevation and the yellow being low elevation, there's about 40 meters of elevation drop across the countryside here. And you can see these linear features, and this is, as I mentioned, a glaciated area. That's a textbook classic field of drumlins. So as you drive across it, in fact, you can see it here. If you're driving your car across that cross-section, you go up and down over top of these drumlins as you migrate across the countryside. It's a beautiful drive. The subsurface, as you can see, is quite complicated. So aquitards that pinch out, various aquifer units. Some places the aquifers are connected, other places they're separated. High variability in the unsaturated zone thickness from 15 to 18 meters or so down to maybe 2 or 3 meters, quite variable. The production wells sit down here in aquifer 3, and that provides you with sort of an idea of what the stratigraphy looks like in the subsurface. And the regional groundwater flow, as you can imagine, from the upland area down towards these production wells as they're pumping away here. That gives you an idea of that. And the last piece of information that's useful as we get into the detailed investigation is what the water quality looked like. So based on that wide-ranging network of wells, one can plot this distribution of nitrate. So the central highest concentration around 16 milligrams per liter, that's as N again, remember, so that's well above the drinking water limit. Down to the edge of this is still 8, and 8, of course, is way beyond naturally occurring concentrations of 1 or 2 maybe would be high that you might see. So highly impacted over a very broad area. There's a scale down at the bottom for you to see that. So with that kind of information in mind, the students were then to tackle the idea of what the leaching rates were through that plot of land that they bought. Okay, so there again is our piece of land and the production wells. In order to determine that, one would need to calculate how much surface water precipitation that infiltrates into the ground actually recharges past the root zone and moves down to the water table. In other words, calculating and measuring groundwater recharge. And with that recharge, what you'd want to know is how much a nitrate is it carrying. So in other words, determining the mass flux of nitrogen through that footprint of land. If you could do that, determine the total number of tons that are leaching through that landscape, one could then take the concentrations in these production wells and their production rate and determine how much that would reduce the impact on those wells. So that was the task. The first group of students, Klaus Haslauer, Lauren Beckeris, and Jamie Koch undertook to do this work. So their approach to it was somewhat unique. They established a series of locations throughout the field. Now, each one of these locations was designed to capture a different location and set of conditions that represented the field site. So lowland areas, upland areas, places where the till sheets were coming right to the surface, other places that were sand and gravel, to try to capture the variability over the area. And at each one of these little sites, what they did is they drilled from the surface down to the water table and below, very carefully collected the core, determined the stratigraphy, installed monitoring wells down at the water table and a little bit deeper. And in the core hole that they drilled down, they put in a continuous PVC tube that could be used to accept a geophysical device to measure soil moisture content. So a neutron probe, in fact, is what was used for that. So each one of these stations then was designed as what they'll refer to as a nitrate flux station. And we had right in the middle here, we had a meteorological station to capture all of the climatic information one would need. And the hope was, and I'll show you how they calculated this, if we could determine the recharge rate at these points and the amount of nitrate that each one of these recharge locations was carrying, maybe we could scale up and integrate this by contouring it to determine what the total loading was. One couldn't sample the whole field, but this is scaling up from these point measurements to determine the loading. So determining recharge is not a simple thing. So the approach they took was to do multiple measurement techniques. The first one was somewhat routine that you would think of, using the climatic data and a water balance equation, an analytical equation, to determine the excess water that doesn't run off, doesn't leave by ET, but is available to recharge. That's a pretty straightforward way that a lot of numerical models do. They did that. They also applied some one-dimensional numerical modeling tools. Since they had detailed geology, they were able to measure the soil parameters and the vadosome parameters quite accurately, or as best they could. They had the crop growth patterns. They used these models to predict the excess water that would move through the profile over the course of the year. And the last technique they used, in order to calibrate these two, they applied a bromide tracer, a dissolved tracer of relatively higher concentration bromide that's not native to the area, on the ground surface in the fall. And then over time, let that bromide migrate down through the profile, pushed by the seasonal hydrology that was infiltrating. So the depth at which it migrated is a direct measurement of the recharge. So the way that would look is the first year you'd see this pulse of applied bromide move down to a certain depth. You know when you applied it, that's the total depth that it moved down to the center of mass. They were carefully measuring the moisture content. So based on that profile then, they were able to calculate directly what the recharge was over that course of the year. And they used that number then to help calibrate their models. They let it go again for another year. So year after year, they were tracking this infiltration rate, and that allowed them to calculate annual recharge across the field. That was the first stage of their exercise. So this is just an example of one of the years. As you can imagine, it's quite variable across the countryside here, depending on whether you're in sand and lowland or upland areas. So quite a bit of variability of recharge. And you can take that then and contour it up, and that gives you an idea over a 300-acre area how variable recharge could be on agricultural land. Okay, it's quite varied depending on, of course, all the conditions we've been talking about. So with that approach, they had the water movement down through the profile. And then the next part of the equation was, could you determine how much nitrogen it was carrying? So if we go back to this profile here, so this shows an agricultural land application here, applying on the surface. Here are the plants in the top root zone here. And then we get to this area here that's just below the root zone, and that's that area that I talked about before, functions like an archive. That's where anything that manages to get through the root zone and start migrating down moves down based on the recharge that pushes it annually. Okay? So when you look in the upper part of that sequence, in the top meter here, what you've got is a highly complex nitrogen cycle going on there. Plants are using N, it's volatilizing, it's being consumed, all kinds of things are happening. Once it gets beyond that root zone, the reactions die off significantly, and really what you have, as long as conditions are maintained, is a fairly conservative tracer migrating down towards the water table. So that sort of gives us a target to look at. And what the students decided to do was to track how the amount of nitrogen stored in that area here between the water table and the bottom of the root zone changed over time. So the idea was that if we started changing the nutrient loading at the surface here, we would systematically see below the root zone a change in the concentration of nitrate in the pore water and a change in the total stored nitrate through that archive of the unsaturated zone. Okay, so here's the approach they took to do that. So every 6 months they would come with the drill rig again and core essentially right beside where they took the last core down through the unsaturated zone to the top of the water table, bring the core back to the lab and split it open, take one piece of it here, wash it in distilled water, determine concentrations of nitrate, bromide, of course, they needed for their tracer analysis. They used the other half of the core to determine soil moisture content, helped to calibrate the neutron probe. And the data, of course, that they got here in this one panel you can see represents, for instance, when you take the moisture content and the total stored N that's in the sample that you measured, you're able to calculate pore water nitrogen concentration. And then if you add up the total amount of nitrogen as you move down through the profile, this is the cumulative stored plot of N below the root zone. So the concept was then, could we track that cumulative profile over time at each one of those 15 stations to be able to determine how the BMPs were working over the course of that long time period? So here's the way it worked. That's when we first measured it, when none of the BMPs had been applied. The first year caused an infiltration, and our hypothesis was, of course, since we're changing significantly the loading of nutrients, that the amount that's migrating through the unsaturated zone would systematically drop. And as time went on, we would slowly replace that unsaturated zone with a lower concentration of nitrate. And it would finally hit the water table, and we'd have our improvement. Okay, that's the concept of it. So I'll show you some of the data. On the right-hand side is nitrate concentration. The red profile is in 2006, if I recall. The green profile is in 2008, so several more years into the application of the lower nutrient loading. You can see a drop from maybe around 20 milligrams per liter on average of nitrate down to somewhere around 10 to 12. Total stored N in the profile, as you can see in that diagram, represents about a 60% reduction through the unsaturated zone. And that's not far off how much we reduce the nitrogen loading. So this little approach of coring right below the water, root zone gave us an immediate estimate of the performance. So that was the metric that we were looking for to be able to determine if this was working or not. So then what the students did, of course, was combine their recharge estimates with their nitrate concentrations on an annual basis, and were able to calculate the total nitrogen flux leaving the bottom of that root zone on that 300 acres. That gave us a total number of kilograms, it turns out tons of N that was infiltrating. So to summarize that little part, when they put it all together in all those 15 stations over that long time period, that change in that BMP change resulted in an average from 20 milligrams per liter through the unsaturated zone down to below the drinking water limit of 8, so a substantial improvement, and something like a total loading reduction from about 5.5 tons over that 300 acres to somewhere just over 2, a 60% reduction. So then, of course, when we show this to the agricultural community, they say, well, that's great, but what kind of impact has that had on our corn production? So thankfully, we had the farm operator that was managing this land here. His task was to track the nitrogen balance continuously. So he provided us, and I brought him to all the agricultural meetings, he explained it to the farming group, that in reality, what we've seen is no reduction in corn. So he used corn as the metric. That's the one that got their most significant attention. So previous to the historical land use practices to the current ones, they hadn't lost production in agriculture over 10 years of change. Okay, so this wasn't just a legacy of what was sitting in the soil profile. This was a significant reduction in N, but maintaining the crop production. So when they said you actually applied half the fertilizer and got that production, that gives me 2 more weeks in Florida. So that's the kind of thing that really hits them, you know, in terms of cost savings on the fertilizer. So with that piece in hand, of course, the municipality were happy that we made that calculation, but the second part of the equation was, what's that going to do to our production wells? Okay, thanks for calculating that, but what does that mean in terms of our water quality? And incidentally, how long will that take? So that moved us to the last phase of this investigation, and that was, how could we predict what the impact on the production wells would be? That's really what the municipality wanted us to do. So in order to do that, we were able to make use of the newly sophisticated numerical models that are available to us. There's some fantastic tools out there. One of them that we used, and there's many others that you could use, is FEFLOW. And FEFLOW allows us to capture all that variable stratigraphy in the subsurface in 3 dimensions as best we could from our coring and our detailed subsurface information, and also allow us to calculate that complex transport through the unsaturated zone. So it's a variably saturated code that allow us to track in time the movement of that change in nutrient loading as it migrated down to the water table. So FEFLOW was a useful tool. So 2 students took on the job of modeling, and they did it in 2 pieces. The first piece was a large regional scale numerical model. That's the red outline. And that model was used to determine the steady state groundwater flow field through that complex 3-dimensional system, with these wells pumping away again at 300 or so thousand gallons a day, big production wells causing this big flow field to change. They calculated it at steady state, and then internally took the results from that external model, applied them to a smaller internal model, carved this out, and in here did the solute transport calculations. So in reality, the outside model provided the boundary conditions to the inner model, and the inner model was run at steady state for flow and transient for the change in nutrient loading. Okay, so the idea then was, here's our little piece of land where we changed our land use practice. Could we use this model to show what the conditions were like prior to the implications or implementation of this change in nutrient loading, and then after, and what impact did that have on the wells? Okay, so this little diagram, just to show you, there's the regional grid, and you can see it's relatively densely discretized, but nothing compared to the internal one. In order to capture that dynamic through the unsaturated zone, we needed to highly discretize it and make sure that we were able to stay within a stable solution here. So this is the grid then that we used to do the solute transport modeling. So here are the results. Let me just show you this briefly here. So this piece of land in the middle, you'll recall we carefully measured what the conditions were like prior to the implementation of the BMPs, and that gave us an indication as so many grams per square meter was infiltrating as N. So if you make the assumption that that 300 acres is probably reasonably representative of the other agricultural land around it, we made that as an assumption, we spread that number out over the top boundary condition of the model, And the area that was the woodlot, and the area of this small, as you see, this small little urban center here, we put a significantly lower leaching rate under those two pieces of land. That's where we were not applying fertilizer. That was the top boundary condition that was not allowed to change. Okay? So the second part of it was then the only boundary condition that we had no control on. Remember that the flow was transported over from the large regional model, calibrated to the data set that we had. The only information we didn't have was how much nitrogen was coming in along the lateral boundaries. Well, going out to the field where we had measured this distribution of groundwater nitrate, that provided the students with an answer for a range for what these boundary concentrations could be. So they simply used that as a parameter to calibrate in order to capture the concentrations in the production wells the way they looked before we started implementing the best management practice. So somewhere between 10 and 12 milligrams per liter in these big production wells. So fortunately, as part of their calibration, they were able to achieve that. So we felt very comfortable we had the mass balance correct in the model. Okay? So the second part of it now, as I show you the end here, is that this area now, since we carefully measured what the improvement was with the BMP, we changed that top boundary condition and let that fresher plume, if you will, migrate down through the subsurface, hit that concentrated plume, and be captured by the well. Okay, so we're looking at this influence of a more dilute plume migrating through the subsurface. When you do that, when they run it to steady state, you'll see that the concentrations in the production wells that we're concerned with drop below the drinking water limit, just barely in one case there, something like a 20% improvement in the water quality. So this was a very good piece of news we could then take to the municipality. And then, of course, the final piece that they had asked for was how long would it take? Well, since we ran that solute transport problem transiently, there's the breakthrough curves at the production wells. This is essentially the breakthrough of that more dilute plume arriving at the wells and modifying the quality of the well water. So as you can see, the first 2 years that they were anticipating their big benefit, essentially nothing happened. And that shouldn't be a big surprise because it had to get its way through the unsaturated zone into the water table and over towards the wells. It took much longer than that for this full production effect to be seen. So it took, we're theoretically saying, somewhere around 2020 would be the final impact. So we took this to the public meeting and thought, well, this is great. We've got all the answers for them. Students all came, dressed up, presented it. And this is what we thought we'd get for a reaction. And of course, that's the reaction we got. So thank you for this nice study, but at the end of the day, we're sitting with these production wells for the next 10 years that we have to wait. So that was a big shock that it was going to take that long for that to happen. In hindsight, of course, it shouldn't be. So they sent us back to the drawing board. So let me show you one little piece here to finalize this. If you look carefully at this diagram, there's a term here called denitrification. So one of the things that happens to nitrate in the subsurface under the correct conditions is that it will break down through natural biological activity. It will be used as a food supply and respiration. So if there's no oxygen around, the right bacteria will use nitrate as a food source. And that process is called denitrification. So it'll take it from nitrate, it'll break it down to nitrate, as we'll show as we move along here. So the process of denitrification is under conditions that are relatively anaerobic, not much oxygen. Otherwise, the bacteria would selectively use the oxygen for this process. The bacteria will take nitrate through this process, break it down, essentially using this nitrate as an electron acceptor to nitrite, which is not which is even worse than nitrate, but fortunately not very stable, through a couple of nice greenhouse gases down to what you and I breathe. And that's a natural process. So the question was, could we get that to occur in the field while we were waiting for that big BMP plume to finally arrive at the wellhead? Could we give them some remediation as such? Okay? So in most natural conditions, and clearly in this one, this reaction will occur as long as you've got the correct environmental conditions and as long as you've got an electron donor that's available. And that electron donor is normally an organic carbon, or a redox species that's available for the reaction. It's very much like a catalyst to the reaction. So you need that. If you don't have it, the reaction won't occur. So looking back at the problem here of a non-point source, remember that source that we're looking at is very broad in nature. It's not like a gas station that may be smaller than the size of this room, that we can put a permeable reactive wall in front of it, put a pump and treat system in front of it. It's a very broad problem that covers a highly irregular loading characteristic, as we said. But one of the things, of course, that production wells do for us that helps us along is that they concentrate or diverge and capture water from a broad area, so the mass gets pulled towards them. So the question was, could we find a location next to the municipal wells where there was a very high stream, high mass flux that we could treat at a level high enough to remove enough to drop the concentrations below the drinking water standard? So here's the process then. So there's the stratigraphy that we looked at before. Here's a cross-section running through the center part of the big plume. And right where that dashed line is, you can see the two aquifers are connected here. And at that location, the water table's not very deep. Two of the main aquifers are connected. The concentrations are very high, and we're right next to the well field. So that represents a little window or a high-speed component of the plume that one could target for remediation. So this is looking at non-point source remediation here. So last couple of slides. What we did was we put in an injection well and an extraction well doublet perpendicular to the flow field and injected that lacking electron donor. In this case, it was just acetate. So it was very soluble vinegar mixed with groundwater, injected into the ground with the idea of stimulating this process of denitrification. So the acetate was pumped into the ground and extracted over here with this well. And once we started picking up the acetate in this well, we turned the system off and let this plume of carbon migrate into the plume of nitrate, hoping to get these folks down here interested in consuming nitrate. Okay, and this is really the approach. And again, none of these videos seem to work, unfortunately, so we won't be able to see that. That just gets you down to the ground surface. So I'll take you here. There's the edge of the woodlot. We're not far, 300 meters in is the production wells. So we installed those doublets the students put in every 5 meters, an injection and extraction well, and then downstream from them put multi-level monitoring wells in order to track this reaction once the acetate was injected into the ground. When the wells were first put in, these multi-level wells showed us that indeed about 18 meters of the aquifer, sand and gravel all the way down, loaded with nitrate, 14 milligrams per liter, all the way through the aquifer, which was a bit surprising on its own. The other piece of information was that this was anything but anaerobic. It was loaded with oxygen. It was 8 milligrams per liter, so nowhere near in the conditions that one would hope to get for denitrification. So very little was going on in the field. The subsurface looks like this, a very high gravel unit in the middle, sand and gravel above and below. Injected here at the screen, migrates down through these multi-level wells, and we track it downstream. So here's the process. About 250 milligrams per liter of acetate is injected into the ground on about 6 hours a day. That's about how long it took. So it goes in, groundwater's pumped out, mixed with acetate, put back down in the well, migrates downstream towards the production wells. And that experiment was run by these students for almost 2 months, and they tracked downstream dissolved oxygen, nitrate, nitrite, as you can imagine, and some of the redox species that were of interest. And here are the results. Interestingly, the oxygen concentrations dropped down in the first week. So by injecting the acetate, the bacterial population grew up and started consuming the oxygen. So the oxygen dropped down in most levels somewhere around 2 milligrams per liter. 1 or 2 units stayed a little higher. When one looks at the nitrate, concentrations were around 14 milligrams per liter. There's the drinking water limit. Again, in a week, once the oxygen was consumed, most levels dropped somewhere down around 4 milligrams per liter. Where we were not able to get the oxygen down low enough, you can see the nitrate stayed very high, upwards of 10 or 12 milligrams per liter. In other words, the bacteria just used the oxygen that was available. It didn't need to go to nitrate. Okay? But if you combine that all together, what you see is that without the treatment, about 1 ton per 5 meter width of the aquifer moves towards the production wells per year in that sort of high-graded part of the plume. By treating it with the acetate, we were able to drop it down in about a half. So only 50-meter wide section of that aquifer treated with acetate would allow us to reduce the concentrations of those production wells below 9 milligrams per liter, and that would happen in less than a half a year. So this process then showed us that we could augment this long reliance on a BMP that takes such a long time to arrive at the production wells with an alternative, of course, which is remediation. So non-point source remediation in that particular case. And then they were much happier with that result at the end of the day.
You didn't have to build a treatment plant to treat all that water.
Absolutely. So it's very expensive. So at the end of the day, when we look at this, I'll just summarize this last two slides here. This shows you that obviously we're sure that this stress on the agricultural landscape is going to continue. Our role as hydrologists is really just starting. It's really a challenging issue. We're going to have a lot to do in this particular problem. But I will say that I'd say that there's an awful lot of positive messages to take out of these types of experiments, that working with the agricultural community, I think we can find a way to balance food production and groundwater quality. I think it's a matter of just using some of our technology that we have. In order to get the agricultural community to adopt it, though, these types of studies are imperative. And the problem, of course, is how long they take to be able to demonstrate and how multidisciplinary those types of studies are. That's the nature of them as we move forward. So I would like to fly you back now from beautiful downtown Waterloo, but Google Earth doesn't want to let me do that today, so you have to stay there for a bit. By the way, it's supposed to snow tomorrow there, so you don't want to be there. Let me just put as a little epilogue, my colleagues at the municipality gave me this plot just a month or so ago with the great news that here was the implementation of the BMPs. A couple of years into it, they didn't see much of a change, and then progressively over the last, this is now up to 2013, those are the concentrations in the production wells. So they're now at a point where, on average, they can put these wells back into production. And so now they're sitting, as you mentioned, they didn't build that water treatment plant, which would now be redundant.
Right. All this was caused because somebody put too much fertilizer on that 300 acres.
Well, on a much broader land area, actually. But at the end of the day, it was not what you'd call too much over. It was kind of routinely what we would use. It was what they were kind of encouraged to use. So it's a matter. Amazing. And that's the win from the agricultural point of view. And that's the part that we're now hopefully being able to get into policy to help encourage them to adopt it. Anyway, so I'll finish with just stating that I had a large number of colleagues that helped me with this. I won't read everybody's name out here from all over. The farmer was a tremendous assistance in this, as you can imagine. Funding came from the federal government, provincial government, and of course from Oxford County, which were the leaders in this, and they were really the impetus behind it all, and some industrial support. And with that, I'll thank you for your patience this afternoon and be happy to take any questions.
We have time for questions.
Made it in time. Please.
Is planting of legumes any type of viable means of getting rid of nitrates?
Yeah. So planting them and harvesting them, in other words. So very much so, because they'll fix nitrogen from the atmosphere. So a lot of it comes from the atmosphere for most of the legumes, and then if it's harvested off, you can remove that. If you leave the roots behind, the roots then will decay and release the nitrogen into the ground. So one of the things about the legumes that's useful is that if you process them correctly, red clover is what he used in this particular case, the remnant root mass provides you with a portion of the fertilizer that's released just at the time that you need it. And it's released slowly. It's not like the soluble nitrogen that's applied in terms of urea or a capsulized nitrogen fertilizer that's so soluble it can be flushed down by a precipitation event. The organic end stays in the root zone for a longer period of time. So it costs to put it in, and you have to do an extra pass to plant it. So there's certainly a cost there, but compared to the amount you save in fertilizer, it was way better off to do it that way. So this whole concept of cover crops is becoming, much more. It's not only for they used to use cover crops, of course, to reduce erosion primarily, but now its benefit as a nitrogen fixer and balancing of the nitrogen cycle is really coming to the forefront. Question? Yeah.
What level of interest did the fertilizer industry have in your study?
Oh, they loved it. So you can see how much we were funded by the Canadian Fertilizer Institute. to be honest, the market for fertilizers worldwide is only going to continually increase. And in order to maintain a sustainable supply all around, the fertilizer companies are behind doing it right. They're not really concerned about the fact that I'm telling you, you can reduce your fertilizer purchases by 30% maybe, and still get the same crop yield. The fact is that that's what's happening, and all the tests are showing you don't need to apply as much. People applied more or less because they were just by nature risk averse, and they didn't want to take the chance of having not quite enough fertilizer to get the best crop they could. You can understand that. It's like an insurance policy. But now that fertilizer is expensive, they're way more concerned about managing it as a resource. And if you can demonstrate that your yield is just as good, and we didn't do that. We let the farm operators manage those fields. So the people that lived right there managed those fields. So we weren't bluffing them. They were the ones calculating, which is really critical, as you can imagine. That really provided them with this insight that you could get away with less fertilizer. But we never really got severe kickback from like bad messages on the walls or anything, phone calls at home with quiet voices or anything. But so we work with them now. That's a good question. Yeah.
Any impact to the drinking water standards, mostly secondaries for taste, odor? Yeah, I know that you didn't add a whole lot of acetate,
Right.
so it's minimal at best based off the distance and the amount of water production coming out of the well. But
Yeah.
was there anything, or did you identify it?
No, so very good point. So we had to work for a year and a half before this experiment was run to demonstrate in the field that if we injected acetate, that when we generated nitrite, which as it turns out is a drinking water level of, I think it's 1 milligram per liter, that was very short-lived in the subsurface, and it would break down. So we were the first student to work on this, Katie. She had to demonstrate that in order for us to get a permit to actually inject large amounts of acetate into the ground. So when you calculated it, the acetate, of course, disappeared at the same rate that nitrogen did because it was consumed as part of this process. But what was produced, of course, was nitrite at a very short distance, about a meter away from the well injection. Nitrite showed up in low concentrations, and then we never saw it from that point on. So it went beyond that part of the reaction. We used nitrogen isotopes to show the enrichment in N15, which is just an indicator that the reaction is occurring. It's not guaranteeing you that it's denitrification, but it's just one more of those little pieces of information that's useful. So the only thing that really showed up was a slight increase in manganese at 7 meters away from the injection. So we went slightly beyond the reaction, the oxygen reaction, in a couple of the layers, and it got to manganese oxidation. But that in itself, the concentrations were so low when you dissolved them in those hundreds of thousands of gallons coming out of the well field, you'd never detect it. So the government allowed us to do that based on the mass balance calculation, showing this. No matter what you did, you'd never put a threat on that public supply well by injecting vinegar. But that took a year and a half to get them to agree to do that. Yeah, which is awesome question. Exactly right. Yes, John.
What about the concept of applying, say, a carbon source, acetate, over the cropland right before recharge?
Yeah, so carry it with it.
Chase it down.
So in reality, in that soil profile, you've got a lot of available carbon. So you're not really lacking that particular source with it. And it's as it moves through the vadose zone or moves through the soil profile, it's relatively reactive. So you probably wouldn't get a lot of it through the root zone. And then on its way down through the profile, you probably wouldn't have enough of it arriving at the water table to be useful on such a broad scale. This way you can at least focus the injection in a smaller, real high flux zone as opposed to applying it over such a broad area, and maybe use less mass and have the most effective application of it. That question was asked many times, that we were looking for ways to better apply fertilizers so that they would break down faster. But you don't really want them to break down in the root zone. But because there's so much oxygen there, the reaction doesn't occur anyway. So it stays in a nitrate form. It goes from ammonia to nitrate pretty quickly, and then it's soluble. So it'll move past the root zone. But it's mostly the scale of it that would be it. Yep, Scott.
David, it looked like you cut the
Sure. So if you actually calculated in fact, we know that because the model, in order to get the mass balance, we had to calculate the flux coming in on the lateral boundaries, and we knew what the total loading was on the surface. So that little 300-acre footprint on the top really only represented 20% of the mass all over it. So the actual capture zone goes so much further out beyond that. So we're seeing just a small input. But the question is then, 300 acres in an area that big is a pretty tiny piece of land. And if you can manage that land in a way that you can still get a great corn crop from it, and that's without affecting anything else on the other land area. Well, all these other farmers are looking at that and saying, well, if I can apply less